Let's see if we can all see it. Maybe not. So apparently you can't see it. I think if I angle the thing, it'll not show it. But yeah, he drew a picture for you guys. It's a little, I call it Pikachu. We'll call it Pikachu. So what we've established so far in chapter 5 is if they give me a polynomial, especially if it's in factored form, that we can graph it without having to use our graphing calculator. So what that does is that tells us what the zeros are, which are those x-intercepts. Where we're headed today is without looking at the graph, can we factor the polynomial? So we're now kind of going backwards from what we were doing. Can we find those x-intercepts when it's not in factored form and it's a much uglier polynomial? So that's section 5.5. Again, we've skipped sections. We will come back and fill in those missing sections next week. The rest of 5.1 is due today. So I noticed that one of you came in and did part 2, but didn't do part 1. So make sure you go back and catch part 1. And then on Saturday, you have both 5.5 and 5.6 due. And then you have quiz number 5 is due on Sunday of this week. A reminder that Pearson's MyLab Math will be down for maintenance next Thursday and Friday, July 2nd and 3rd. You will not be able to log on at all, so plan accordingly. So let's get into 5.5. I did email out the notes yesterday afternoon. Hopefully you took a look at them or have them handy. So we're going to go find the real zeros. A reminder that the real zeros don't involve I. So in terms of solutions here, no complex answers again. So that really means that we won't see I. So when we hit a square root of a negative, we're going to stop today. We add those in tomorrow, and most textbooks typically do this in 2 separate sections. So, okay, so what you know? So what we know right now is if I gave you f of x is equal to x squared plus x minus 6, and I ask you to find the zeros. Okay, what I'm really asking you is to solve f of x equal to 0. So in other words, you would come in and take that function. You'd set it equal to 0, and that would give you the x-intercepts, which are also the zeros, which are the solution. And you already know how to do that. You can come in and factor it. Factors into x plus 3 and x minus 2. So you get x equals -3 and x equals a positive 2. So again, the zeros would be the -3 and the 2. The x-intercepts would be -3, 0 and 2, 0. And another way of looking at it is that the solutions are x equals the -3 and x equals 2. So all of these kind of mean the same thing. It's just a matter of what they are asking for in terms of how you write the answer. So, but we already knew that. That was nothing new. We did this, in fact, when we did the quadratic equations last week. So we know how to do that. The problem's going to be is that now all of a sudden our polynomials are not going to be factorable. So what happens if we have f of x equals x cubed plus 8x squared plus 11x minus 20? So there's nothing we have in our toolbox right now that lets us factor this polynomial. So we're kind of stuck. So we need some new techniques. So that's what section 5.5 is all about, or how to go about factoring when it's not factorable. So again, there are a lot of theorems in this section. If you actually are reading the textbook, you'll see a lot of boxes with theorems in them. So we're going to go through them. You need to know how to use them, not necessarily what the name of them are. I don't believe in memorizing theorems for you guys. So the first one we're going to do is something called the remainder theorem. And again, I'm not going to write it down. It's in the book. It's on the handout. What we really want to know is what it tells us. So the remainder theorem is our first one. Okay, what the remainder theorem says is if you have a polynomial function, and if f of x is divided by x minus c, where c is a constant, then the remainder is f of c. And it's like, okay, that's nice. I have no idea what that means. So we're going to try and explain it. So example 1 asks us to find the remainder. And you have no idea why we want a remainder. So it's kind of like we're evolving a theory here. If f of x equal to, and that's not going to fit over there. The polynomial I just had on the board, the x cubed plus 8x squared plus 11x minus 20, and we're going to divide it by a couple of things, is divided by, and part A says x minus 1. Okay, so in pre-calculus, because a couple of you are headed to pre-calculus, you'll review long division. So one method, and please don't write this down because I don't want you to do this. One method of doing this problem would be putting x minus 1 on the outside, putting that x cubed plus 8x squared plus 11x minus 20 on the inside, and physically doing the long division. Well, that's a little bit more than we need to tackle. So instead, what the remainder theorem tells us is if we come in and evaluate the polynomial at 1. Now, where's my 1 coming from? Again, I'm taking that factor of x minus 1. I'm setting it equal to 0, and that would give me x equal to positive 1. So again, because it's being written as a factor, I change its sign when I go to work for it. It's the same thing we did when we graphed parabolas. It's the same thing we did when we graphed circles. And it's what we did yesterday when we pulled those factors out. So we're just going to plug 1 in. So 1 cubed plus 8 times 1 squared plus 11 times 1 minus 20. 1 cubed is 1. 1 squared is 1 times 8. 1 times 11 is 11 minus 20. That's 9 plus 11 is 20, minus 20 is 0. So the remainder theorem says if we did the division, so if we divided f of x by x minus 1, the remainder would be 0. So in other words, it divides into it evenly. So it saves us having to go through that long division process. So it's wonderful. It's quick. It's easy. It lets us look at remainders without doing anything else in terms of division. So, and you're saying, again, why do I need about the remainders? So just hang on. Why we need remainders is important. Let's do another one. So there's a part B to that problem. So same initial function. And I want to find the remainder if I divide that function by x plus 3. So again, it's written as a factor. So the remainder theorem says instead of actually doing the division, we can come in and plug in a negative 3. And again, notice as I pull it away from the x, I change its sign. So that would be a negative 3 cubed plus 8 times a negative 3 squared plus 11 times a negative 3 minus the 20. Okay, that one's uglier. A negative 3 cubed is a negative 27. Watch your order of operations. I need to square the negative 3 first and make it into a 9 before I do the multiplication. 11 times a negative 3 is a negative 33 minus 20. That's 72 minus 33 minus 20. Okay, so negative 27 and negative 30 is going to be a negative 60. That makes it a negative 80, and the 72 I get a negative 8. So if I've done my arithmetic correctly, I get a negative 8. So again, what is this saying? So it means if we divide f of x by x plus 3, the remainder is a negative 8. So any problem about what the remainder tells us? It says we can either do the division or we can just plug the number in and get what the remainder is. Okay, remember our whole goal is to be able to break apart this polynomial into its factors. That's our whole goal here. We want to be able to factor it using different methods. Okay, so the next theorem is called the factor theorem. And again, you do not need to memorize the names of the theorems. Okay, the factor theorem says if you have a polynomial function, then x minus the constant c is a factor if and only if f of c is equal to 0. So x minus c as a factor. I don't know why I'm having problems writing today, but apparently I am. Wednesday. If f of c is equal to 0. Okay, so I'm going to step away from the handout for just a minute. Just a few seconds ago, we had f of x was equal to x squared plus x minus 6 on the board. And we know that this factors into x plus 3 and x minus 2. Okay, what the factor theorem says is if we were to evaluate the polynomial at that -3, so I'm just going to plug in the -3. I can use either one of them. I'm just picking the first one. So I'm plugging in the -3. That'd give me a 9 minus 3 minus 6. Sure enough, I get 0. So the factor theorem says that if you have a factor, you know it is a factor because when you evaluate it at that 0, you get a 0. So if I came in and took that same polynomial and evaluated it at any other number than the -3 or the 2, so if we plug in a 1, we get a 1 squared plus 1 minus 6. That'd be 1 plus 1 is 2, minus 6 is a -4. Notice that that's not a 0, so it's not a factor. So x minus 1 is not a factor. So you'll notice what we're kind of sneakily doing is we're learning to break this down without actually having to use our factoring rules that we learned a long time ago. Okay, so let's come in and do the one that's on the handout. So it does say on the handout the theorem actually has 2 separate parts to it, and that's because it's an if and only if statement. So if f of c is equal to 0, then that means x minus c, so in this case x plus 3, is a factor. And if x plus 3 is a factor, then f of -3 is a 0. So it's both ways. It's a two-way street. You can look at it from either point of view. So this is how we're going to determine whether or not factors are actually factors or numbers are actually zeros. So example 2. Says use the factor theorem to determine whether or not x minus 2 is a factor of f of x equal to 4x to the 4th minus 15x squared minus 4. We have 2 ways of doing this. We're going to do the first way is what we just got through doing. So the functional notation, so method 1, is to come in and find f of 2. And again, notice that I switch the sign as I pull it away from the x. So if you write it with an x, you have to switch its sign when you go to plug it in. So that's 4 times 2 to the 4th minus 15 times 2 squared minus 4. 2 to the 4th is 16 times 4 is 32. 2 squared is 4 times 15. 4 times 15 is 60. Minus 4? Okay, I didn't do something right. 16. Right, 2 to the 4th.
64 is meant for 2 to the 4th minus 4.
Thank you. It's like, okay, I've got an arithmetic mistake because I'm expecting it to be a 0. So thank you. 16 times 4 is 64. Thank you for that catch, Rich. Okay, so 64 minus 60 minus 4 is, yes, indeed, 0. So what that establishes, because f of 2 is 0, then x minus 2 is a factor. Woohoo! Yay! Okay, that's one method. So there's nothing wrong with that. The problem is that we're going to need more information to find other factors. This only gives me one factor. I need a lot more of them. In fact, I need all 4 of them by the time we're done. So we're going to go to a second method. Method 2 uses synthetic division, which should be in your past somewhere. If not, then guaranteed by the end of today, you'll have it down. So synthetic division. And what you should be saying to me is, wait, you told me I didn't have to do the division. You don't. We're going to use a fake division process. So what synthetic division does is it puts over here in the box what you're evaluating the function at. So we're evaluating the function at a positive 2. And again, that's coming from that x minus 2 factor. You put a positive 2. Then right next to it, I'm going to list the coefficients of my polynomial. So the first coefficient is a 4. It has no x cubed term, so I'm going to put a 0 as a placeholder. The placeholder is important. It needs to be there. You then have a negative 15. You now need another placeholder of 0. And then finally, the last coefficient is a negative 4. So you'll see the 4, the negative 15, and the negative 4 are sitting there. Because there's no x cubed and because there's no x term, we have placeholders of 0. Okay, now we're going to write above and below it. So I'm going to leave a little room up here and then I need room below it. So that's the setup. That's how you set it up. To actually do it, what you're going to do is bring the first number straight down. So whatever that first coefficient is, it comes straight down no matter what. Now we're going to multiply. So 2 times 4 is 8. It goes in the next column. And then we're going to add that column. That's why it's called synthetic division. We're not actually doing any division. We're doing multiplication and addition. So, okay, well, 2 times 8 is 16. I'm repeating the process. Negative 15 and 16 is 1. 2 times 1 is 2. Adding that column gives me 2. And 2 times 2 is 4. And adding that column is 0. The last number down here is my remainder. And if f of 0 is 0, then x minus 2 is a factor. So we want the remainders to be 0, which is what we want. So that gave me the same result as plugging the 2 into the function, but it also gives me something really, really important. These numbers sitting right here become the coefficients on the depressed equation. So I'm kind of skipping ahead, but I think it's good to put it in right here. So that 4 belongs to an x cubed. I'll have an 8x squared, I'll have a 1x, and a positive 2. If we had done the long division by putting the x minus 2 on the outside, this on the inside, and going through the long division process, we would end up with, as a polynomial answer, 4x cubed plus 8x squared plus 1x plus 2, with a remainder of 0. Okay, this cube right here is coming from the fact that we started with a 4th degree, and when we divide it out an x, we go down to a 3rd degree. So we refer to this whole thing as the depressed equation. And it's depressed because we've depressed it by 1 degree. We've lowered it by 1 degree. Great. So that's synthetic division. We will do a lot more of it today and tomorrow. So you'll get used to it. So again, method 1, just plug the 2 in, see if you get a 0. The second method is to use synthetic division and make sure the remainder is 0. Either one works. And honestly, in some cases, this is quicker because you'll notice that I made an arithmetic mistake when I did it plugging the 2 in. So it's entirely up to you. So what we know right now is this. This polynomial back up here, this 4x to the 4th minus 15x squared minus 4 factors into an x minus 2. That's what we found when we plugged in the 2. And then it also has as a leftover the 4x cubed plus 8x squared plus x plus 2. So you can kind of see where we're headed with this. If the idea is to break it down into nothing but the factors, then I've already got one factor. Now I'm going to go to work on what's left over as a polynomial and see if I can do it again. So our next theorem, moving on. Any questions so far? Okay, looks like we're doing okay. So next theorem. Is the number of real zeros. And it simply says that a polynomial function cannot have more real zeros than its degree. So example 3 is quick and short. We want to tell how many zeros, the maximum number of real zeros of f of x equals, and I keep picking on this guy. It appears several times. In other words, How many zeros can this have? Well, it's the maximum degree. So the highest degree we see is the 3. So the possible maximum number of real zeros is that 3. In other words, if we go to solve this or graph it, the most times it can cross or touch the x-axis is 3. That's it, which is why quadratics can cross the axis twice and lines can cross the axis once. So, and again, we're talking about the x-axis because these are the x-intercepts. The next theorem, so is the rational zeros theorem. Told you there were a lot. This is number 4 already. Rational zeros theorem. Okay. So in the box on the rational zero theorem, it basically says, let f be a polynomial function of degree 1 or higher. It doesn't work for a constant, but degree 1 or higher. Each of their coefficients is an integer. If we look at p over q in lowest terms, this tells me the types of rational zeros. And it's really hard to do it from the wording. So we're going to jump right in and do example 4 to help you make sense of this. So f of x is equal to 2x cubed plus 11x squared minus 7x minus 6. Okay, so the coefficient out in front is what we're going to refer to as q. The last or constant at the end is going to be what we refer to as p. So the possible rational zeros. So in other words, the possible numbers that could be zeros that are rational numbers. And what, again, a rational means is no radicals. So fractions are fine, decimals are fine as long as they're terminating or repeating. So this gives me a list of possibilities. Well, what we're going to do is all factors of p. So we go all factors of p. Over all factors of q. Okay, so I need all the numbers that divide evenly into p. Well, 1 divides into 6, 2 divides into 6, 3 divides into 6, and so does 6. So all possible factors of 6 are 1, 2, 3, and 6. I do the same thing with the 2. All possible numbers that divide evenly into 2 are 1 and 2. And then because we have to worry about x-intercepts on both sides of the axis, we're going to put a plus or minus in front of it. Then what I'm going to do is take that and make it to a physical list of numbers. So what I do is I take the first number and put it over both of the second numbers. So 1 over 1 is 1. 1 over 2 is 1/2. 2 over 1 is 2. 2 over 2 is 1, and I've already got it listed, so I'm not going to list it again. 3 over 1 is 3. 3 over 2 is 3/2. 6 over 1 is 6. And 6 over 2 is 3, and it's already listed. Okay. So what this list is a place for us to start in order to try those possible factors of our polynomial. So this gives me a list. So what this is saying is that if you factor this down, the only real rational factors it can have would be x minus 1 or x plus 1, x minus 1/2 or x plus 1/2, or x minus 2, x plus 2, x minus 3, x plus 3, x minus 3/2, x plus 3/2, those kinds of things. So the only possible factors that are rational numbers, and again, that's anything that does not include a radical, and we're leaving off all the i's today, are in that list. You're saying I still don't get where we're headed. That's okay. Give me a few minutes. We are going to get there pretty quickly. Okay, so that's all the theorems. The factor theorem, the remainder theorem, the maximum zero theorems, and the rational zeros theorem. And now what we're going to do is kind of put it all together and start solving polynomials. So I'm on the last page. Finally, we're ready to actually find the real zeros. The following steps will help guide you through the use of the theorems to find the zeros. So what we're going to do is work a problem as we're writing the steps on the board. Again, the steps are on the sheet, but it's easier just to work one as you're doing one. So I'm up to example 5. What we want to do is we want to come in and find the real zeros of f of x equals x cubed plus 8x squared plus 11x plus 20. So the same one that we've been looking at for quite a while here. Okay. And then once we've done that, we're going to write it in factored form. So, okay, so step one, we're going to determine the number of zeros. Determine number of zeros. So because it's a third degree polynomial, at most it has 3 zeros. They don't all need to be real numbers. Some of them could have i's attached to them, but for today, we're only going to find the real zeros. So that's the first step, determine how many zeros you've got. Our second step is to come in and use the rational zero theorem. So we're going to list the possible rational zeros. So this is the P over Q. So P is always the last number, so I need all numbers that divide evenly into 20. It's not as big of a list as you think it is. So 1, 2, 4, 5, 10, and 20. And those are all the numbers that divide evenly into 20. And you'll notice what I'm doing is I'm starting at 1, I'm going to end at 20, I'm just mentally going through them in my head. Notice they kind of line up in terms of pairs, 1 times 20, 2 times 10, 4 times 5. Okay, that's over all possibilities for Q. Q is always the first number or coefficient, which in this case is a 1, which does not impact our list. So I didn't even need to write it. 1, 2, 4, 5, and 20. There it is. Okay, so if this graph crosses the x-axis at a whole number, I'm sorry, an integer or a fractional value, it's one of those numbers. Or all 3 of those numbers. So 3 in that list. Okay, so far so good. I've just been laying groundwork. That's all we're doing. Okay, step 3 is the big one. It's the one that we get to do because we've got technology in our lives. At this point, what I'm going to do is I'm going to come in and graph the function. So I'm going to come in and graph y equal to x cubed plus 8x squared plus 11x minus 20. This is the step that's going to slow you down. Okay. So hopefully everybody's got something that they can use as a graphing calculator, whether it's your phone or not. And do you know how to graph on your calculators?
Yes.
I got one yes.
Yes.
Yes. Adam's a yes. Matt?
Yeah.
Woohoo! Okay. So somebody go graph it. So again, what you're graphing, you're going to go into the y equal to and literally plot x cubed plus 8x squared plus and so forth. Looks like somebody was playing with my calculator last night. Okay. Now the graph is not part of the work or the answer. It's just what we're using as a tool to make it a shorter problem. Okay. So when you're done, you get something that looks like this. And then it looks like this. I've got my window set from -10 to +10 and -10 to +10. That's the standard window. So that's what I've got it set at. So you get something that looks like that. And again, without that graph, I literally have to sit here and try all these numbers, right? And I don't want to do that because I want to be efficient. So what I'm after is, it doesn't matter which one I pick, I usually start on the left side. So the question is where is this? So can somebody tell me where it looks like that is at? You should be able to count your tick marks over.
-5.
Yep, -5. I just realized I left out a 10. Okay, so now we're going to use x equal to -5 in our synthetic division. So in the box, I'm going to put that -5. Notice I am not switching its sign. When I go to write it with an x next to it, I would switch its sign. But here we're just pulling it off. Now I'm going to use the coefficients. So I have a 1, an 8, an 11, and a -20. So again, those are the coefficients off the original polynomial. Okay, first step, bring the 1 straight down. You don't really need the arrow. It's just me showing you bring the 1 straight down. So 1 times -5 is -5. Adding that column gives me a 3. 3 times -5 is a -15. Adding that column gives me -4. -4 times -5 is a +20. Adding that column gives me a 0. That's your proof that -5 is a 0. The picture is not proof. It's just a tool. Yay! Does everybody see what we did? So we're letting the calculator do the grunt work. If I didn't have that picture, I literally would have to sit here and try each of these numbers in the synthetic division until I got to a 0. Now, once I found one of them, I'm done with the synthetic division because I know that the depressed equation down here is, so this is a 1x squared plus a 3x minus 4. So that's a quadratic. And at that point, that quadratic can get set to 0. You can either factor or use the quadratic formula. Factoring is quicker, so I'll factor. Well, this factors into x plus 4 and x minus 1. So I know that x equals a -4, which is this next 0, and x equals 1, which is the other 0 sitting over there. Okay, so to finish off the steps, so step 3 was to graph it. Step 4 is to use the synthetic division. So here's step 4. Each time that a 0 and a factor is found, then repeat the process on the depressed equation. And don't forget to use, if possible, the factoring techniques you already know. So once I got it down to a quadratic, I simply then worked off the quadratic because it's quicker than doing synthetic division again. But now I need to answer the question. So the answer to the question, the zeros of the polynomial, and it doesn't matter in what order, we have -5, we have the -4, and we have 1. And you'll notice that all 3 of those numbers appear in our list of possibilities. So that was wonderful. They also want me to write it in factored form. So f of x is equal to, that -5 is going to come from an x plus 5. That -4 is going to come from an x plus 4. And that 1 is going to come from an x minus 1. Woohoo! Yay! We did it! So we took a polynomial that we could not factor prior to today, and we've been able to break it down into its factors. And then don't forget that factoring is a form of division. So what we've really done is divided this polynomial into its individual factors. So, okay, that's the process. They're not difficult. They are long only because it's very repetitive, because you keep doing the same thing over and over and over again. So because there are all kinds of little quirks, we have to go do quite a few of them to give you all those little quirks. Any comments on example 5?
I'm okay.
Okay. Let's go tackle example 6. Example 6, I just erased what I need. Example 6 is the same as example 5. The only thing that's going to change is the wording. So it wants me to solve x cubed plus 8x squared plus 11x plus 20. That's the polynomial we just had equal to 0. So the only difference here, the process would be the same. So we would use the same process. And that means whether they're asking me to solve it or whether they're asking me to find the zeros, the process is the same. And we know that x is equal to a -5, a -4, and the +1. So whether I ask you to solve it or to find the zeros, I'm asking you to do the same thing. So this depends on which way the book's got the wording going for a particular problem. Example 7 gives us a new polynomial to work with. So f of x is equal to x cubed plus 3x squared minus 2x minus 6. So we want to find the real zeros and then use the zeros to factor it. So, yeah. So let's go through our steps again. I'm going to start labeling them just because I think it helps us. So the first step is to figure out how many zeros we're looking for. So the number of zeros is 3. They might be real, They might be a mixture of real and complex. They could be rational with no radicals, or they might have radicals. We don't know. But the number of real zeros is that first exponent, which is 3. The next step is to do your list of P over Q. These are the possible rational zeros. So we need all numbers that divide evenly into 6. That would be 1, 2, 3, and 6. Q this time is 1 again, so I don't have to do anything with it. So far, no fractions. That's a good thing. Okay, step 3 is to graph. Okay, so go graph it. I'm going to graph it too, so I've got it. So x cubed plus, and I can just go in and change the coefficients. Minus 2, and then minus 6. X cubed through x squared minus 2x minus 6. And you'll notice that these graphs look exactly like what we think they should look like. It's a third degree polynomial. It's got a positive leading coefficient. Starts below, ends above, right? What we're doing is from yesterday is we need to find where those x-intercepts are. Okay, this one's a little sneaky. So I'm going to start with this guy over here. And again, it just always start on the left side. So where does it look like that guy is at? So physically from your graph, we can read that one, and it's over there at?
Is it -4?
-4, but -4 is not my list.
Yeah.
So that's why I'm not going to use it. I think it's -3. 1, 2, 3. So in mine, it looks like it's at -3. So again, I'm going to use this list to help me decide where it's at. So we're going to go use -3 and see. We'll know whether or not that's true because we'll get a remainder of 0 or we won't. So when we use the -3, we've got a 1, a 3, a -2, and a -6 as our coefficients. So we'll bring down the 1. 1 times -3 is -3. Adding gives me 0. It's okay. Don't freak out when you get a 0. 0 times anything is 0. Adding that column is -2. -2 times -3 is a +6, and adding gives me a 0, which is what we want. So we need the 0 there. It worked. So it is a -3. Again, if we tried -4, this number over here wouldn't be a 0, so that's how I know it doesn't work. Wonderful. Great. Okay, what's left down here is my depressed equation. So what is this 1, this 0, and the -2? If I put the x's back on them, we're going to get what? That's a 1x squared. And again, that's coming from the fact that we started with a cubic, a third degree. You knock off 1x, you get an x squared. Now we have 0 x's, and then -2. Okay, that's the same thing as x squared minus 2, which we're going to set equal to 0. Okay, well, I can solve that pretty quickly. Can't we just move the 2 to the other side? So that'll give me x squared equals 2, and then I'm going to square root both sides. So x equals plus or minus the square root of 2. So the other 2 zeros that are appearing right here and right here, this one's a positive square root of 2. This one is a negative square root of 2. They are decimals, 1.4 something, 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 right? So again, notice these guys do not appear in the list. These are irrational zeros. They're still zeros, and they are still real. They're just not going to appear in that list. So that's why you have to go through synthetic division. You can't take a guess at what those guys are because they're not rational. They're irrational. Whew. Okay, to summarize it, or to make sure we've got the answer. So the zeros. And again, in any order, we've got a -3. We've got a positive root 2, and we have a negative root 2. And I don't really need the plus on the positive root 2. So there's the zeros. In factored form, our polynomial is an x plus 3, an x minus the square root of 2, and an x plus the square root of 2. And there it is in factored form. So it's a pretty powerful thing to be able to do if you deal with polynomials, that is. So far, so good?
Yes.
You're having fun and you just don't know it. 2 more. so example 8, same directions. This time our polynomial is f of x equals 5x cubed plus x squared plus 10x plus 2. Be really careful when you go to work these, because I'm assuming that you go to paper and do stuff on paper while you're doing the online homework. Make sure you copy things correctly, because I can't tell you how many mistakes are made because you miscopy things. So, okay, so through our steps again. First step, how many zeros will this one have? So when I'm all done, how many zeros should I have?
3.
Yep. Again, I don't know that they're all real, but it has at most 3 zeros. Okay, step 2 is my P over Q list. This time it's a little more ugly. Okay, P is the last number. What are all the numbers that divide evenly into 2? 1 and 2. We do have a Q this time. It's our 5. So what are all the numbers that divide evenly into 5? 1 and 5. Wow. So that means as far as real zeros that are rational are, we would have a 1 or a 1/5. We're going to have a 2 or a 2/5. So if you think about seeing 1/5 and 2/5 on your graphs, those are really close together. So, okay, step 3 to graph it. Okay, you go graph it this time. I'm not going to graph it. Actually, I need to graph it because I want to make a point. Darn. So, 5. Tell you, the graphing is the slowest part. Plus 10. Okay, so this time, my picture looks like that. Is that what you guys get? Okay, probably looks straighter than that. Well, wait a minute. This thing has 3 zeros. I'm only seeing 1 0. So does everybody agree it's only crossing the x-axis once? Crosses x-axis once. Okay, I know that because it's crossing that it's an odd multiplicity. So a couple of things could be happening. It could be that I have a single 0 and it occurs 3 times. So like x, that's either the 1/5 or the 2/5. It's not a 1. So it could be x minus 1/5 cubed, right? Or what could also be happening is that we have complex zeros, things that involve i's, which don't appear on the x-axis. So 2 things could be happening here. We won't know until we go try something. Okay, so now we're going to go try something. So from the graph, we're going to use, okay, which one do you think it is? It's not a -1. It looks to me like it's less than -1. Do you want to try the 1/5 or the 2/5?
1/5.
I'm sorry, which one? 1/5?
1/5, yeah.
1/5? Okay, let's go use the -1/5. Now, this is the first time we've used a fraction, but I have faith in you guys. Things will work out fine. So again, I picked up my coefficients. If they're a negative, make sure you include negatives, but mine are all positive. So I'm going to bring down the 5. 5 times a -1/5 is a -1, because the 5s would cancel, leaving you with -1. That's a 0. 0 times anything is 0. Bring down the 10. 1/5 of 10. Well, 5 goes into 10 twice. Bring up the negative. That's a -2. And there's our 0. So sure enough, you get a 0. So if you tried the -2/5, again, this answer wouldn't be 0. So we know we've got one. So our depressed equation then is a 5x squared plus the 10. There's no x term because of the middle. If we set that to 0, we're going to get 5x squared equals a -10, or x squared equals a -2. And here's where the issue comes in. When I go to square root both sides, I'm going to get plus or minus the square root of -2. That involves an I. Those are complex zeros. So that's a complex 0. So on tonight's homework for section 5.5, they don't want those at all. All they want is the real zero, which is a -1/5. Tomorrow's section is going to add this back in. So we're going to do a lot more of this tomorrow with a couple of other twists in there. Okay, so to answer the question, the real zero is -1/5, and that is it, only one of them. The other two, to make up my total of 3, are complex. So in factored form, f of x factors into, and this is where I'm going to pull a fast one on you guys. If I do x plus 1/5, which is what you probably want to do, and then I'm going to pick up the 5x squared plus 10. Did we see what it is? Okay, and if I FOIL this back out, doesn't that 5x squared times that x give me my 5x cubed? However, this guy down here, we know that we can pull a 5 out of it. So I'm going to pull the 5 out and call it x plus 1/5 times x squared plus 2. So in other words, I'm doing whatever factoring I can do and still leave things looking. So there it is. Woohoo! Okay, one more, and it's only because we haven't done a 4th degree one that we need to do a 4th degree power. So just so you have one in your notes. You could go up to any degree power. They just get uglier and uglier or more complicated. We won't do anything above a 4th degree. No. That's also true in pre-calculus. Okay, so our last one we're going to do, f of x equals 2x to the 4th plus x cubed minus 7x squared plus minus 3x plus 3. So the same process, the only difference is now it's a 4th degree. So we know in step 1 that we're looking for 4 zeros. Step 2, our P over Q list, we're going to have factors of 3, which are 1 and 3, over factors of 2, which are 1 and 2. So I got fractions floating around again. So I've got a 1, a 1/2, a 3, and a 3/2. So 1, 1/2, 3, and 3/2. So. Okay, the next step would be to graph it. We are expecting it to look like a 4th degree, which means it should start and stop on the same side. So it should look like a W when we're done with it. So oops, that's the phone. That's not going to graph it. Sorry about that. Equals 2x. You guys are probably quicker punching these in than I am. It looks something like that. Again, exactly what we kind of expect it to look like. It should start above and end above because it's an even degree with a positive coefficient, so it does. Okay, so I'm going to compare that picture to my list. And what number do you want to try first? Let's shoot for this guy over here. What does this one look like it's at? I think that's the one that's at 1. No, -1. Sorry. Looks like this guy over here. I think that's at -1. So from the graph, we're going to try a -1. So we have a 2, a 1, -7, -3, +3. And again, what I'm doing is comparing the picture to my list and seeing, well, that looks like it could be at, that kind of thing. So we'll bring down our 2. Multiplying is going to give me -2. That's a -1. Multiplying is a +1. It's -6. Multiplying is a +6, which gives me 3. Multiplying is a -3, which sure enough gives me my 0. So I guess correctly. Okay, the problem is that this right here is 2x to the third power. So this 2 that's sitting right here is a 2x cubed. I can't factor that. So I need to use synthetic division again to get this down to a quadratic. So this is not a quadratic. Right? So we're going to use synthetic division 1. So I go back to my picture. I don't have to redo anything. I'm going to compare the picture to my list again, and it looks like a positive 1/2 is going to work. So again, comparing the picture to my list, I'm going to go try a 1/2. So I'm saying that this guy right here is a positive 1/2. So another fraction. So we'll bring down the 2. 2 times 1/2 is 1. It gives me my 0. 0 times anything is 0. -6, half of -6 is a -3. Sure enough, we get our 0. Okay, this was the x cubed. This is 2x squared minus 6. And again, set it equal to 0 and solve from there. Running out of room. So 2x squared minus 6 equal to 0. So 2x squared equals 6. X squared equals 3. So x equals plus or minus the square root of 3. So the square root of 3 is about 1.7. So over here is a negative 1.7. This is a positive 1.7. So the key here is that if you have a 4th degree, you have to go through the synthetic division twice to get it down to it. So our zeros, in no particular order, are the -1, the positive 1/2, the square root of 3, and the negative square root of 3. And in factored form, f of x would be equal to x plus 1, x minus 1/2, x minus root 3, and x plus root 3. Okay, and the last thing to mention is I have a slight problem here. If you FOIL this back out, which you will not do, please don't do that. You take this x times this x times this x times this x, you will get your x to the 4th, but you're not going to get the 2. Somehow or other, that 2 has disappeared. So what I'm going to do to make sure that that 2 is accounted for is I'm going to take that 1/2 and rewrite that as a 2x minus 1. Notice that if I solve either one of those, I'll get a 1/2. If I said x minus 1/2 to 0, or if I said 2x minus 1 to 0, they're both going to give me an x equal to 1/2. The only reason to do this is to recreate that 2 that's the leading coefficient. And then the other ones stay the same. Why did I not have to do that on that last one? It's really coming from this right here. We divided this 2 out up here. That's where that 2 got lost, but I need to account for it somehow. So on the last one, we didn't have that problem because we recognized that we pulled the 5 out of the 5x squared plus 10. So kind of a little weird twist at the end of that. Okay, and that's it. So that's all you're doing in 5.5. The homework is actually not all this end part. So some of them that just ask you, tell the maximum number of zeros, what's the P over Q list, and then you'll start doing the full-blown problems. So, and then tomorrow all we have to do is add in the complex solutions. So it's hopefully a little bit shorter tomorrow. So any comments or questions?
I'm okay.
Okay. Go have fun with it. Enjoy the rest of your day. Bye.
Bye.
Have a good day.
Thank you.